to the final lesson of Chapter 1. This is Lesson 1.7 on solving absolute value equations and inequalities. There's an awful lot in this lesson. We're going to be looking at solving those problems that involve both equations and inequalities. So in our experience with solving equations, that's pretty straightforward. But we did just spend our last lesson talking about solving inequalities. And now we're going to take a look at what happens when we plug those into problems involving absolute value. All right? Now, the definition of absolute value is the distance from a number to 0. And I'll just say a number x to 0. And so, therefore, the absolute value of x is equal to the distance from x to 0. Now, distance can't be negative, right? So the reason the book defines it as using distance is because distance has to be greater than or equal to 0. I guess it could be a distance of 0, but distance has to be positive, all right? And so as we're talking about distances, the reason that we define absolute value as the distance between a number and 0 is so that we can always be concerning ourselves with just the positive version of the value x. And so the absolute value of, say, -2 is 2, because the distance from 0 to -2 is 2 units. The distance between 0 and 5 is simply 5. And so in order to avoid a lot of confusion, one of the other ways we talk about absolute value is we say, look, whatever sign it is, who cares? When we take the absolute value, it makes it the positive version of that number. All right? An extraneous solution is, another word for extraneous is garbage, all right? And so as we talk about a garbage answer that we got by solving the problem the right way, but getting a solution that doesn't check. So we're going to say a solution that doesn't check. So as I'm taking a look at a problem, if I solve a problem properly and I get two different solutions, I should always be plugging my answers in and checking. We don't do a very good job of that sometimes because we know that when we got our answer, we got x equals 2, and so we go, okay, well, x is 2. We should be taking a look at our solution, and that will be more apparent as we take a look at some of these absolute value equations as we start to solve these. Okay? All right. The equation absolute value of x is the same thing as the distance from x to 0. So if we subtract those two, the distance from x to 0, that distance between x and 0 is some distance k. And so visually we think about the number 0, and here's negative x and here's positive x, because those two are both k units away from 0, whatever that number is. And so we say that x minus 0 is equal to negative k, or x minus 0 is equal to k, and again, subtracting 0 effectively means we don't do anything, and so x is either equal to positive k or negative k. Now, that's when we're subtracting 0, and so now we're going to be taking a look at something a little bit different. Now we're going to say, how far is it from x to some number b? Well, the distance between x and some number b is our number k, and so again, here you're saying that the distance between b and negative x is k, and between b and x is k. So x minus b is equal to negative k, or x minus b is equal to positive k, and so if I add b to both sides of this equation, I get x is equal to b minus k, or x is equal to b plus k. And so we get our two solutions that way. Now, this might be a little bit more confusing in practice because you can't really memorize this. This doesn't necessarily work all the time, but we can think about this as saying, look, the distance between some number x and b is this value k. Well, it's either positive or negative of that number. And so we're going to take a look at a couple of examples here and see if we can't make some sense out of this. So what we're saying here is we're saying, look, the distance between x and 3 is 6. So we want to know what are two numbers that are 6 units away from 3. All right, and so that's the way that we should be reading the problem. But really, that gets a little bit confusing. Another way I like to think about it is to say, look, if there's two numbers that I can take the absolute value of, let's forget about what's in here for just a second. Pretend you can't see that whatsoever. Now there are two numbers that can be in that absolute value sign such that when I take the absolute value of it, I get 6. And those two numbers are either 6 and negative 6, because when I take the absolute value of 6, I get 6. When I take the absolute value of negative 6, I get 6. So what we're going to do then is we're going to set the number, this in here that I've just drawn over, we're going to set that equal to either negative 6 or is equal to positive 6. Because there are two numbers that this absolute value can be equal to and get 6. It's either 6 or negative 6. So I set what's in the absolute value signs equal to either 6 or negative 6. And so now we're going to add 3 to both sides, and so this becomes plus 3, so that's 6 plus 3, which is 9. And over here we're going to add 3 and add 3, and so this becomes negative 6 plus 3, which is negative 3. So the solutions are 9 and negative 3. What that's saying, it says these are the two values of x that are 6 units away from 3. Because again, the distance from x to 3 is the way that they're teaching it to you here. So here's 3, and then 6 to the right of that would be at 9, and 6 to the left of that would be at negative 3. All right? And so the two numbers that are 6 away from 3 are 9 and negative 3. Now again, I don't really like to look at it that way because this to me is a little bit confusing. What I like to do is just simply here set what's in the absolute value equal to either 6 or negative 6 and go from there. All right, so why don't you try the next two problems here. Go ahead and pause your video and give them a shot and come on back and check your solution. Okay, welcome back. In the first example, again, the absolute value of x is equal to 5. That says there are two numbers that x could be where I take the absolute value of it and get 5. Well, it seems that would make sense that x is either equal to 5 or x equals negative 5. So on a number line, here's negative 5, here's positive 5. Now, we're not shading either direction, and the reason we're not shading is because this is an equal sign, so my two solutions are those two dots. All right, so we don't have to worry about shading anything. In the second example, we now have x minus 5. Absolute value of x minus 5 is 2. Now, according to the book, they're asking what are the values of x that are 5 away from, the distance between x and 5 is 2, so the two numbers that are 2 away from 5. In our head, that's 7 and 3, but we'll check that solution here. What I do is I say x minus 5 is equal to 2, or x minus 5 equals negative 2. So again, what's in here, either when I made it positive, it became 2. So that means what's in here either has to be positive 2 or negative 2. Add 5 to both sides. So you get x equals 7. Add 5 to both sides again. And again, x equals, and this is negative 2 plus 5, which is 3. And so here's 5. Okay, that's my starting point. And if I went 2 to the right of that, I'd be at 7. And I went 2 to the left of that, I'd be at 3. And so my two solutions are 7 and 3. So that makes sense. All right, to solve an absolute value equation, this is kind of where we get into this idea of finding an absolute value equation a little bit more in depth of what we were doing before. Use these steps to solve an absolute value equation. The absolute value of ax plus b equals c, where c is greater than 0. And again, they're saying c's have to be bigger than 0 because when you take the absolute value, it's got to be positive. That's why c has to be more than 0. So, like we did before, we say, look, whatever's in the absolute value, either set it equal to positive c or negative c. Whatever that number is, it's got to be either positive that or negative that, because when I take the absolute value, it makes it positive. The second step is to solve each equation, and then check your solution in the original absolute value equation. So, make sure that when you get done, you always check your answers in the original absolute value equation. You're going to be making two equations here. Don't plug your answers into your two equations. Plug them into the original and see if they check. All right? So let's take a look at an example on the top of the next page then. It says the absolute value of 4x plus 10 is equal to 6x. Make sure, and again, they're going to tell you this here because it's our first time doing it. They're not quite so nice to you later on. So you want to make sure that you're paying attention to checking your solutions. So what did we say? We said whatever's under here, when I made it positive, it became 6x. So that means whatever's under here, which happens to be 4x plus 10, is either equal to 6x or negative 6x. So again, it can equal 6x or negative 6x. So to solve both of these, you're going to be subtracting 10 from each side. So again, minus 10. Oops. Let's rewind that. I'm not going to be subtracting 10. We're going to be subtracting 4x from both sides because we want to get all of our x's on one side. And so this becomes negative 10x, and this becomes 2x. And so, again, we're going to subtract 4x from each side. We're going to solve for x. So in this case, we divide by 2. And so it says 5 equals x. Divide by negative 10. And so this is negative 1. So we now have to check to see if our solutions are okay. So first we're going to try the 5. Let's plug the 5 in here and here, because again, there are two different occurrences of x. 4 times 5 is 20, and 20 plus 10 is 30. And over here, 6 times 5 is 30. The absolute value of 30 is 30. And so since 30 does equal 30, that solution's okay. Let's try the other one. Let's try our negative 1. Plug in negative 1 there and negative 1 there. This becomes 4 times negative 1, which is negative 4. Negative 4 plus 10 is 6. 6 times negative 1 is negative 6. When I take the absolute value of 6, I get positive 6. Positive 6 is not equal to negative 6, and so we have to reject negative 1 as a solution. We can keep the solution 5. That one's okay. It only has one solution. And so the negative 1 becomes what we defined earlier as an extraneous solution. We did all the right math. We just got a solution that doesn't make sense when we go back and check it. All right, so again, pause your video, try the next example, come on back and check your solution. All right, welcome back. Let's go ahead and try this. Again, what's in the absolute value has to be equal to 11 or negative 11. So we're going to say 2x plus 5 equals 11, or 2x plus 5 equals negative 11. Solve each equation separately. This is 2x equals 6. Divide both sides by 2, and x equals 3. Minus 5 from both sides, you get 2x equals negative 16. Dividing both sides by 2 tells you that x equals negative 8. So now to check these two solutions, again, our two solutions were 3 and negative 8. And so we're going to say the absolute value of 2 times 3 plus 5 is equal to 11. This is 6 plus 5, and the absolute value of 6 plus 5 is 11. And so that solution's okay. Let's try the other one. Absolute value of 2 times negative 8 plus 5 equals 11. This is the absolute value of negative 16 plus 5. And negative 16 plus 5 is negative 11, and the absolute value of negative 11 is positive 11. So both of our solutions checked here. All right, what about the next one? Again, we've got 3x plus 18 equals 6x. So either 3x plus 18 equals 6x, or 3x plus 18 equals negative 6x. And so minus 18 from both sides. Sorry, let's not do that. I think I did that last time too. Minus 3x from both sides to get all of our x's on one side. 3x equals 18. Divide both sides by 3 and x equals 6. Minus 3x from both sides, you get negative 9x equals positive 18. Divide both sides by negative 9, and x equals negative 2. Now, I'll let you check the x equals 6 on your own. That one does work. But when I try negative 2 here, this solution here becomes 3 times negative 2 plus 18 equals 6 times negative 2. Well, that's negative 12. And on the other side of this, I mean, we can go through the math here, but whatever this is, when I take the absolute value of it, it's going to be positive, right? And so positive cannot equal a negative. So this one here, we're going to reject that solution. So our only solution is x equals 6. So again, that negative 2 is an extraneous solution. So what about absolute value inequalities? Absolute value inequalities are just a little bit different here. And when you're looking at an absolute value inequality, now you're looking at solving something that has a greater than or equal to, less than or equal to, etc. Very similar to what we did in the previous lesson. So the absolute value of ax plus b is less than c essentially says this. We've got to find some absolute value where its value is smaller than c. Well, that means that it's going to be between negative c, wherever negative c and positive c are, this ax plus b is somewhere between negative c and positive c, because again, it has to be smaller than c, but greater than negative c. So this is going to lead to a graph that is an and. All right? So when you're dealing with a absolute value problem, if it's a less than sign, that's going to give you an and graph. And so when you set up your absolute value, you're going to set up an absolute value and. As we talked about last section, again, this is an and problem because it's putting ax plus b between negative c and positive c. For ax plus b is greater than c, when I take the absolute value of that, that's saying, look, we want all the numbers that are bigger than c when I make them positive. Well, that's going to be all the numbers to the right of c and to the left of negative c. Because again, when I take the absolute value of numbers down here, those become numbers that are larger than c, which are these numbers over here. So again, this is an OR graph, and so it's going to be either ax plus b is smaller than negative c, or it's going to be greater than positive c. So greater than signs and absolute values lead to ORs. Less than signs, or again, less than or equal to signs will lead to ANDs. So let's try an example. This one is an example that says that ax plus b is greater than c. And so since the value is bigger than c, that says that I want all the numbers that are this way or that way. And so this is going to be an OR problem. Either 2x plus 5 is less than negative 3, or it's greater than positive 3. So again, we're going to say here's 3. Instead of using c, let's just use negative 3 and positive 3, and it's all the numbers that are that way. Now this is not my solution graph, but it just gives us an idea of where to start. In both cases, we're going to be subtracting 5 from both sides. So this is less than negative 3. This is greater than 3. And I'll just work one at a time. We're going to subtract 5 from both sides. So this is negative 8. And when you subtract when you subtract the 5 from both sides, you get 2x is less than negative 8. And from there, we're going to divide both sides by 2. And so that shouldn't be there. This is now negative 4. All right? On the other side of this, we're going to subtract 5 from both sides, so I get negative 2. When I divide both sides by 2, I get x is greater than negative 1. And so my solutions are then all the numbers that are less than negative 4, or all the numbers that are greater than negative 1. And so here's the numbers that are less than negative 4. We're not dealing with less than or equal to because it's strictly greater than to begin with. And all the numbers that are to the right of negative 1. And again, notice that my graph here is an OR graph because I was comparing all the absolute values that were bigger than 3. Well, again, bigger than 3 is bigger than positive 3 or less than negative 3. So that leads to an OR. Again, write this big on the side. This is an OR because of that. Okay, let's try the next one. In the next example then, we're going to take a look at the next one in example 4. This one now is dealing with a less than sign. So ax plus b, if it's going to be less than or equal to 4.5, that means it's going to be between 4.5 and negative 4.5, because again, if it's less than 4.5, it's all the numbers this way. And again, that means those numbers have to be bigger than negative 4.5, so this is going to lead to an AND graph. So again, it's AND because of that. So again, we're between negative 4.5 and positive 4.5. And so when I add 1.5 to all 3 parts, I get x is between negative 3 and positive 6. And so the solution is between negative 3 and positive 6. Now the reason they're using the word inclusive here is because they're saying you're including them because it was less than or equal to. So again, because of the equal to sign, we're going to be coloring those in. This is now negative 3, positive 6, and again, the values are between them. And so you should be getting a solution like that. All right, pause the video, try the last 2 examples, and we'll be right back with solutions for them. Okay, so here we are on the last 2 examples here. Again, for number 5, you've got a greater than or equal to. And so let's think about what that looks like. My absolute value stuff is more than 7. So that's these numbers over here. But when I'm considering absolute value, the numbers that are also bigger than 7 are the ones to the left of negative 7. So this should be an OR graph. So I'm going to say x minus 2 is greater than or equal to 7, or x minus 2 is less than or equal to negative 7. Add 2 to all parts. And so I get x is less than or equal to negative 5. In this one, I get x is greater than or equal to 9. All right, and so here's negative 5. Less than or equal to that is going to be all the numbers to the left. Here's positive 9 right there. Again, greater than or equal to, so color it in, and all the numbers to the right. Notice again, because it was a greater than sign, it led to an or, because again, I wanted all the numbers that are greater than 7 or less than negative 7. In the next one, I want all the numbers that are less than 9. So now, the numbers that are less than 9 are the numbers that are this way, but they stop at negative 9. So again, here's 0. It's somewhere between 9 and negative 9 if the absolute value is less than 9. So that leads to an and graph. And so since that's leading to an and graph, I'm going to put 4x minus 1 between negative 9 and positive 9. Okay, add 1 to all 3 parts. I'm going to slide over here. Negative 8 is less than 4x, which is less than 10. Divide all 3 parts by 4. And you get negative 2 is less than x, which is less than 2.5, or 5 halves, or whatever you want to call it. This is an exclusive because this is strictly less than, so we've got negative 2, open dot, positive 2.5, which is going to be right in there, so we're going to use an open dot, and we are going to shade the in-between areas because this is an and problem, again, because it's putting x between negative 2 and positive 2.5.